Hello, Math 20-1. We're continuing our journey with the learner outcomes of sequence series, and we are in geometric sequences continued, part B. And this is going to be about some of the deeper applications to questions in geometric sequence. So you got to hold on to your hats because you're going to have some algebra as you look at the learner outcomes. You can see that we're going to be dealing with some algebra. So geometric sequence have some really cool applications. We talked about biology and so on, but there are fractals and all kinds of amazing things that happen in geometric sequences. So first off, let's look at just a basic question that we could be dealing with. And in this case, we're given a geometric sequence and it's telling us it is, but we can also see that when we look at these clearly, as we look and compare these, it clearly is multiplying by 2 as we go along. So it is geometric even if they didn't tell us that. Determine an expression for the general term. So because it's geometric, we use the t at n because they're talking about general term. So in the t at n formula, we can see that the common ratio is going to be 2. We can also see that if we use this geometric formula that we talked about last day, we get 4 times 2 to the n minus 1. However, yesterday we talked about how you cannot do 4 times 2 is 8 to the n minus 1. That would be really bad. But what we can do is do something a little more wise. We can use something called same base method and change the 4 to a 2 to the 2, which then goes with this 2. And now we can use the laws of exponents, which says if we have the same base, we can add these two exponents together. And in a nice reduced form, we can now see that we can simplify our general term to something like that. So it's different than what we talked about yesterday, using our algebra skills. So using that general term, we can say, well, if we're looking for term 9, we simply go 2 to the 9 plus 1, which is 1024. Or if we use the other version of the formula that we used last day, we still get the same version, right? Which is 1024. All right. So just using algebra to simplify the general term. What if we had a little bit funkier looking sequence like this? Now you might say, well, I don't even know. Radicals, they scare me. I'm not sure what I'm going to do with those. We still have to consider what kind of sequence this is. It's telling us it's geometric, but are we sure it is? When you divide each of the terms, you'll notice that, yeah, term 1 is 2. It says we're looking for term 9. Are we sure that the common ratio is root 3? Do you believe that? One of the things you should probably do is check it, but it did say that it was geometric, but I want you to get in the habit because not everything is always going to tell you it's geometric. In this case, we're looking for term 9, so we plug in. Well, let's just go back to this ratio for a second. How do you know for sure that ratio works? Well, try two of them. Obviously, root 6 divided by root 2, looking at your math 10, that's clearly root 3. When you look at, say, the next one, you might say, well, holy cow, Mr. K, 3 root 2 divided by root 6, and you might go, whoa, that looks very different. That does not look like root 3. And remember what we talked about, that if you have in math 10, you have to rationalize the denominator. So when you multiply top and bottom by root 6, you now end up with 3 root 12, 3 root 12 divided by 6. And when you reduce this, we can see that we've got 3 times 2 root 3 all over 6. And now 3 times 2 is 6 root 3 all over 6, and the 6's cancel out, and we end up with just root 3. So I know that seemed pretty complicated, and don't forget simplifying entire radical simplex mixed form. In the end, we do have our common ratio of root 3. So there is a common ratio. All right, so we reviewed a little bit of math 10. Now that we're, again, continuing on our travel to find term 9, we plug in term 1 is root 2, the common ratio is root 3, and since we're looking for term 9, we end up with a term of 81 root 2. All right, and remember, don't forget the skills we learned, that simplest mixed form, and we kind of saw it over here as well, and we were just checking to see whether that was a common ratio. Well, now we've got a music application. Well, as we look at music, in this particular context, it's talking about the frequency of the piano board, of the keys on the piano board form a geometric sequence. Cool. Determine the common ratio of the geometric sequence produced by the lowest key A at 27.5 hertz, and I don't know if you've heard of that word before, but you'll see that again in Math 30-1 when we talk about trig functions, and to the fourth key of C1 at 32.7 hertz. So we can look at this in a couple of ways, but if we use the formula, so this is one strategy. If you use the formula, you could carry on if we feel comfortable. You don't have to wait for the PowerPoint. But when we look at these keys, well, we can see that term 1, we'll call A term 1, and that's 27.5 hertz. We don't know the common ratio, but we do know that the one they're talking about, term 4, has a hertz value of 32.7, and that's term 4. So if we plug these unknowns into our formula, we end up with a formula that looks like this. And so now we simply solve this for r, and the only way to get rid of the cube is to take the cube root, and when we do, we get the cube root of 32.7 over 27.5. Now this is an exact value. This makes us happy, but it isn't very useful in terms of using that number. It's not very handy. If you wanted to use a computer or something, you could. So we tend to put it like this, and notice the approximate sign. That's not really the exact value of r, but we do say it's approximately equal to 1.06. All right? And so that's using the formula. All right? Another student might simply go and say, you know what, I like to just use common sense. And so a student might simply just map out the situation. Term 1 is equal to 27.5, and then down the road, term 4, I know it doesn't look very good when you write on PowerPoint, is 32.7. And so therefore we've got 2 spaces in between for us to find or have our frog jump to get to that 4th term. So clearly we can see that if my frog was jumping by multiplying by r, that without using the formula, just using common sense, a person would say, hey, to get from 27.5, you multiply by r cubed to get to 32.7. And then you would solve that equation the same way you had, right? So there's different ways of approaching it, and some of us can just use the formula, and some of us can just use common sense, depending on which works best for you. All right, continuing on, in a geometric sequence, a little bit more intense, I suppose, question. In a geometric sequence, the 6th term is 972, and the 8th term is 8748. So as a puzzle, they're giving us 2 terms to kind of work with, and now we have to figure out Ti, R, and Tn. So again, there are multiple ways that you could approach this question, and you could more than welcome to try it on your own and then come back to notes. But here's one way that you might try it. Well, they're telling you that term 6, and I'm a big fan of just writing down what they told you in notation. So term 6 is 972. It's right. And they tell you term 8 was 8748. All right. Well, if you map this out in terms of what does it look like, well, term 6 to term 8, as we talked about before, to get from term 6 to term 8, you simply multiply by r twice. So if you look at our pattern here, right, to get from term 6, you must multiply by r twice. Multiply by r, multiply by r. So using common sense, 8748, to get from 972 to 8748, you must multiply by r twice. Cool. When you plug in what you know, clearly r squared ends up being 8748 over 972. So don't forget the rules of radicals. Obviously, r can be either plus or -3 based on us and our knowledge of square roots. You must always consider both square roots. However, up in the corner here, it says that, by the way, r has to be greater than 0. So therefore, taking that into consideration means that the only one we really have to consider is the positive value of 3. And therefore, if r has got to be 3, then we can work this formula backwards to find out what T1 is. So term 6 is term 1 times r to the 5. And therefore, if we solve it for T1, we get 972 divided by 243, which is 4. Finding the general term, we go back to our formula and plug in T1 and R, and there's really nothing we can, there's really nothing we can do to simplify like we did in the previous question. You cannot change 4 into a base of 3, so you're kind of stuck in the mud on that. That's as good as that's going to get. And certainly don't put that as 12 to the n minus 1. All right? All right, crew, on we go. Next. Next, we're talking about a photocopy, and this is where when you start doing real applications with real situations, you really got to be clear on the number of terms versus what your target really is. So be careful we don't start blindly using the formula. So a photocopy reduces a picture to 75% of its original size. Cool. So they're reducing it. If it's originally 40 centimeters long, find its length after the 10th reduction. All right, now that's an important thing to consider. 10th reduction, what does that mean? 10th reduction, how many terms is that? Is that the number of terms, or just be careful? That's come up a couple of times now. So sometimes it's helpful just to look at a map of the situation. Now is, if we thought of terms, now is time 0 or 1, and as you copy, if you copied it once, that would really be term 2, and copying it twice would be term 3. And so after the 10th reduction, what are we really looking for? We're really looking for the 10th reduction is really the 11th term. So the 10th reduction is really the 11th term. All right, so we need to be careful how we use this. So obviously when we go to the formula, nothing really complicated. Common ratio is 0.75, and after the 11th reduction, the picture will be 2.25 centimeters long. Cool. Take that into consideration as you do all these questions from now on. A car is valued at $30,000. That makes sense. It depreciates 20% in value each year. How much is the car worth in 6 years? So again, look at these things, and I want you now just ponder before you hear it from me. Ponder, what is the common ratio? What is R? Is R 20%? What does that mean? And 6 years, is it really 6 years? How will I use the formula, and what term will that be? All right. All right, so you've had some time to think about it. Now as you move forward. Well, now is 1 and 2, 3, 4, 5, 6, 7. Obviously, if it's 6 years from now, we should be considering term 7. And again, it's not always going to be at 1. Ponder to make sure. The other thing is that if you lose 20%, the common ratio needs to be what you have. And so notice that the common ratio is not 20. The common ratio is 0.8. And that is because if you lose 20%, what you have left is 80%. And so every year you have 80% of what you had in the previous year. Now that we have that, the actual answer is pretty straightforward. So that, the value of the car is $7,864.32. All right. And ball drop is one of the more, I guess, common applications. And we could easily do a lab on this and so on. But if you dropped a ball from a height of 100, after each bounce, it rises to 40% of its previous height. So sometimes the best thing to do is get a real visual picture. So if you notice, this is actually a visualization of what the ball would look like in terms of the height of it and the number of bounces traveled. So if you just watch, if the ball starts at 100 and traveled bounce, 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 eventually the ball is very low. So what we're really looking for is what is the height that's reached after each of these bounces. It started at 100. After the first bounce, how high did it get to? It got to a height of, I think this scale is a little off, it got to a height of 0.4, sorry, or 40 meters in this case. After the second bounce, it got to a height of 16 meters. So it's less than half of the height that it starts from every single bounce. All right, less than half of the height. So that's what it would look like. We can watch it one more time. And so bounce, 2, 3, 4, 5, 6, and so on and so on. All right, so that's really what's going on in this question. So if we carry on, what's the relationship of the height of the bounce to the number of bounces? Sorry, the relationship forms a geometric sequence, and we need to ponder the common ratio and so on. If a ball is dropped, and this clearly is not a picture like you saw in the last one, because these ones aren't following the 40%, but let's pretend this diagram doesn't match it, but when we look at this, a ball is dropped from a height of 100. After each bounce, it rises 40% of its previous height. Cool. Write the first term and the common ratio of the geometric sequence. Well, clearly the first term, it's starting at 100. After one bounce, it's only 40%. So here's where you're thinking, is it 60, is it 40? And what do I have left in terms of height? I have 40% left. So therefore, the common ratio is 0.4. If we were to write a general term for this sequence, we simply plug in these knowns into the formula, and we end up with t to the n equals 100 times 0.4 to the n minus 1. What height does the ball reach after the 8th bounce? And again, here's where you want to ponder, okay, 8th bounce. Wait a second. Does that mean it's the 8th term? Is that really what that means? Or is it the 7th term? Or is it the 9th term? Ponder that, and it helps to look back at the diagram. What's the first term? Has it bounced on the first term? And the answer is, well, no. So technically, the second term, this is now, that's no bounce. This is after one bounce. So if you're going out to the 8th bounce, it's actually going to be the 8th bounce is going to be the 9th term, okay? And if that doesn't make sense, that's where you ask Mr. Zotner and Mr. Komatiski in class tomorrow, okay? So it does mean that n equals 9, and term 9 is 0.066, which again, we got to watch for units. It makes more sense to express this in terms of centimeters, which is equal to 6.6 centimeters, all right? Now part D, a ball is dropped from this height, same question. After how many bounces will the ball reach a height of 41 centimeters? All right, so now you're bouncing, you go, I wonder when it reaches. And that might have some significance in terms of the context of the question. Maybe after it's bounced that high, the game stops or something, I don't know. But in this case, they want to know after how many bounces will it stop, will it bounce less than 41 centimeters, or how many bounces will it reach that approximate height? Okay, well, might be handy to convert that to meters, so we're dealing with the same units because it starts with 100. It starts with 100 meters, so we better deal in the same units. Now, we have our formula. We have t to n is equal to 100 times 0.4 to the n minus 1. And now, when we substitute that in there, we've got a formula that looks like that because the final term we want is 0.41. And if we were to solve this for our question, we now end up just divide both sides by 100, and we're trying to get at n, and that's a problem. What strategies could you use to determine the value of n? Right? One of the things that a student might try is trial and error. So you keep plugging in values of n until you get something less than that, right? Another suggestion might be this. So here's where I'm just going to turn off PowerPoint for a second, and I'm going to come back here. But another suggestion would be to fire up your calculator. So why don't we look just kind of like the, oopsie. So if you go to, I want that PowerPoint back on. So if you go to your graphing calculator, again, we're dealing with this question, you go to your graphing calculator and you type in y equals, and why don't you just type in the general term, y equals 100 times 0.4 to the x minus 1. So that is the height of the ball after every bounce, right? I've just typed in that general term. And if you go to table set and you think of a geometric sequence, we can only start at the first term when n equals 1, and we'll go up by ones because it doesn't make sense to go by decimals. We can only deal with natural numbers. And now don't look at the graph so much as look at the table. And if you go to the table, you can see, well, there's 100 meters, and after one bounce, the second term is 40 meters, and then 16 meters. So this is, I guess, a fancy way of doing trial and error. Now, where are we interested in? We're interested in it when this thing is less than 0.41 meters. Less than 0.41 meters. So when does that happen? Well, it happens after after it's 0.40 after the 7th term. So that would be the 6th bounce, right? We'll go back to our PowerPoint now, and after the 6th bounce, if you use the table idea that we just did in our calculator, all right? If we look at this example, determine the value of x, which makes 2 and 2 to the x and 2 to the x minus 4 a geometric sequence. What does that make a geometric sequence? Well, the first thing we should probably remember is that a geometric sequence is a geometric sequence if and only if it has a common ratio. That's the definition. So that must mean, we talked about this when we talked about justifying in class yesterday, that means if we take the first two and divide them, we should get a common ratio. And if we take the second two and divide them, we should get a common ratio, and they should be the same. You've got an equation now, and there's only one variable, so we should be able to cross multiply these and end up with a solution. If we look at each of these, 2 to the x divided by 2 to the 1, this one, becomes 2 to the x minus 1. And if you subtract these two, right, I don't know if you can see where they came from, but this is a result of the fact that you subtract 2 to the x minus 4 minus x. This becomes that. And this one, 2 to the x minus, this is 2 to the 1, so x minus 1 is what this quotient becomes. And therefore, you got a pretty nice little equation. And the only way that this statement can be true is if x minus 1 is equal to minus 4. Therefore, the only way this could be true is if x equals minus 3. And if x equals minus 3, go back, and therefore the terms of the sequence are 2, 2 to the minus 3, 2 to the minus 7, and so on. Or 2 and 1/8 and 1 over 128. All right? Cool. This ends our lesson and some pretty intense questions with some good algebra. So make sure we ask some questions tomorrow if it didn't sit well with you. Have a good night.